Morning everybody. This is Kung Fu Physics, where we are steadily working our way through practice physics GRE problems. I have another mechanics problem for you today. It is number 8. Number 8 off of the 1986 exam. So 1986 exam, number 8. If you got it, look it up. It's looks something like that. It's going to be a little fuzzy. My print-off of the 86 exam is a little fuzzy. Apologize about that. So let's get right into it, because I do have a lot to talk about this problem. Now, glance at the answers gives us forces in newtons, and I would recognize this in my head as being what I would call an order of magnitude problem, because that's all that's varying amongst those answers. So you do have to be cautious with a problem like this to not mess up a decimal place, obviously. So let's start the problem. Number 8, a 5 kilogram stone is dropped on a nail and drives the nail 0.025 meter into a piece of wood. If the stone is moving at 10 meters per second when it hits the nail, the average force exerted on the nail by the stone while the nail is going into the wood is most nearly. Okay, so the best way, I believe, to solve this problem is using work energy. And the equation that I would say is most appropriate is the following. And you may have seen this in different forms. Okay, so the change in energy, in other words, the change from an initial situation to a final situation in energy, and that includes both the kinetic and the potential energy terms, is going to equal any work done by a non-conservative force, so a non-conservative force acting over a distance. Basically, this is saying that that non-conservative force is dissipating energy, is one way to look at it. When you have a frictional force, the energy is lost, and for example, a frictional force, there's other types of non-conservative forces, I'm sure, but a frictional force, that energy gets lost in the heat of the molecules that get heated up due to the friction, for example. And that's, I think, the best way to solve this problem. After we finish, I guess I can maybe discuss some of the other ways that maybe are possible ways to solve this problem. But I think this is the clearest, most obvious way to proceed with this. So let's go ahead and get started with it. I want to draw a diagram for me. It helps me clarify things in my head. The initial situation, we have this stone, and I'm going to draw speed lines on it. It just has made contact with this nail, let's say. And this nail is that distance, 0.025 meters. And then our final situation, the nail has slammed down into the wood with the stone on top of it, and everything's still. There's no motion at that point. So I need to find my initial and final kinetic and potential energies, and I'm going to set those equal to the work done by the non-conservative force. I want to look at the energy of the stone and the work being done on the stone. And what I'm going to claim is that the nail is doing work. The nail is a non-conservative force that's going to be doing work on that stone. And so the initial energy I'll do here, and it's an I, and the final energy I'll do here. The final energy is pretty easy, because certainly I have no kinetic energy. If I set my baseline for my potential energy down here, then I would certainly have 0 potential energy, and so the final energy comes out pretty quickly as 0. My energy initial, I have 1/2 mass of my stone is 5. V is 10 meters per second, so I get 1/2 times 5 times 10 squared. Okay, and so I get 250. I'm sorry, let me put in the potential energy. And you will probably be irritated at me if you've seen this problem before or you've worked this problem before for doing this, and maybe rightfully so. But is there potential energy? Is this stone a little bit higher than it is here? There is potential energy. So let's put it in, right? So the mass is 5, G is 10, and H is that, I'm going to use 25 times 10 to the negative 3. Scientific notation, useful, of course, in order of magnitude problems. Okay, so that gives me two terms there for my kinetic and potential energy. And I get 250 for my kinetic energy term plus, and then if I multiply that through, 25 times 5 gives me 125. So I get 1,250 times 10 to the negative 3, which is 1.25. Ugh. Now, if you're a super genius, as many of you are that are going on to grad school in physics, you're probably pretty good at math, and you can probably realize that you want to dump that to simplify your calculations, and that you are justified in dumping that, especially in a order of magnitude problem like this, where it says, specifically in the problem, it says while the nail is going into the wood is most nearly. It doesn't say exactly, it says most nearly. We are justified in dumping that potential energy term, but just to be thorough, I wanted to put that in there. If the problem was a little different, and if this distance, for example, was very great, you would certainly not be justified in dumping that. 250, 1.25, it's obviously very small compared to the rest of the energy. So ultimately, I would say the right way to do the problem, the way that the test maker envisioned doing the problem, is dumping that term and just making an approximation and saying that the initial energy is equal to 250. Okay, so my change in energy is going to be final minus my initial. So what I would say is that delta E equals minus 250, and that equals the work done by a non-conservative force. Now, so when I look at the problem here, the nail, the distance, if I drew the distance as a vector, it's moved from there to there. So the distance is going down. The force is going back up. So I would say this is like, force, and that's my average force caused by the nail onto the stone, and that's going back up. Force dot distance. Okay, so if I call, I have to pick if I want the distance going down or up. So let's say since the distance is going in the negative direction, my distance vector would be going down. I'm going to call that a negative 0.025 meters, and then my negative signs will be gone. Makes sense to me that way. And so basically the negatives drop out. I get 250 divided by 25 times 10 to the negative 3, and certainly be careful with your decimal points in this problem. So 25 goes into 250 how many times? 10 times. And then I get times 10 to the negative 3, but when I divide by that, I just change the sign of that, so it becomes 10 to the 3. And so I get 10,000 equals my average force. This is the average force on the stone by the nail. That's not what's asked for in the problem. What's asked for in the problem is the average force exerted on the nail by the stone. Now, fortunately, those two are equal and opposite reaction pairs, right? If this nail is acting up on the stone, then certainly the stone is acting down on the nail. It's an equal and opposite reaction pair, so it's the same thing, and this would be our answer. Is this one of the answers? We check. Looks like to me it's answer D, 10,000 newtons. That would be the answer I would pick. So that's it. That's problem number 86. As I said before, there are some other ways to solve the problem. Maybe looking at the average acceleration, using some more fundamental basic motions of kinematics, and I would say that it's worth scouting around and maybe looking at some of those other ones, if nothing else, just to review some of your basic kinematic equations and make sure that they're ingrained. But the way that I've done the problem here hopefully makes sense to you. I'll hold that up one more time. And it is a little tricky problem. There are a couple times where you can mess it up, and I would say it's not one of my favorite problems. It's that little extra term of the potential energy and just understanding what it is. I'd say this is a little trickier of a problem for as how simple the math is. It's misleadingly tricky to actually understand what's going on. So review work energy and non-conservative forces and things like that, and practice doing problems like that would be my advice. So study hard. Catch you next time.